Lecture number 2, the geographic grid. It's a location system of intersecting lines, lines of latitude and longitude, you may be familiar with, specifically developed to locate precisely any place on Earth, right, which is a sphere. And so I'm going to begin with lines of latitude, all right, and they have another name. They're also called parallels. You can say parallels of latitude, or so like the 40th parallel. And they're called parallels, right? Because every line of latitude drawn is perfectly parallel to one another, all right? And in this example, they're I think, drawing in lines of latitude maybe in 10-degree increments. But you can draw in 1 degree perfectly parallel to the equator, and 2 degrees, and on, right? And so, on a map, on a flat map, these are the lines that are horizontal on a map, but on the globe, on a sphere, I mean, you would say that these are the lines that run, west to east, or you could say east to west, either way, right? All right, let's talk about the numbers, the counting system of lines of latitude. It was determined long ago that since we have 2 natural reference points, the poles, the North and South Pole, that we would start counting lines of latitude at the midpoint between the poles. And so what we wind up doing is dividing the Earth into equal halves, creating a northern hemisphere, all right, or northern latitudes, and then south of the equator, southern latitudes, right? And so we start counting at 0, all right, at 0. Now, the maximum reading is 90 degrees, all right, and that's just a point. That's just a point at the North Pole and the South Pole. So that's kind of an exception to, being lines, but that's not really that important. But we count lines of latitude, and so, for example, there's the equator, 0 degrees, and this would be 10 degrees, 20, 30, 40, 50, 60, 70, 80, and 90 is the point. And so that's the maximum reading, and just the northern hemisphere is shown there, all right? Now, since each line of latitude is perfectly parallel to one another, all right, it represents an equal distance on the ground. Say if you're driving, north or south, all right, and if you're driving 70 miles on the ground, north or south, you are actually driving a distance of about 70 miles, all right? We just kind of round it off. It's actually 69.4 miles equals 1 degree of latitude. And, I live in Baton Rouge, and I drive about 70 miles back and forth from Thibodaux to Baton Rouge when I come on in, and I'm basically, driving, 1 degree of latitude, right, on my way back and forth, driving about 70 miles. And so that's just a little tidbit of information. But another thing about latitude is that we're going to be using our location in Louisiana, South Louisiana, and we'll, throughout the semester, be comparing our location to the rest of the world. All right, and as it turns out, the latitude of New Orleans, all right, works out pretty perfectly. All right, as it turns out, 30 degrees. All right, 30 degrees. This has to go down. All right. 30 degrees is the latitude that runs right through New Orleans, right? A nice, even, rounded number. Nice, even, rounded number. And so we're always going to be comparing other locations on Earth we're at 30 degrees north latitude using New Orleans or South Louisiana. So that's going to be something like that. And then, you could actually kind of figure out, how far we are, say, from the equator, all right, by knowing the distance of 1 degree of latitude. And so you just use 70 miles, multiply that by 30, all right, 30 degrees, and so 7 times 3 is 21. And so how far is New Orleans from the equator? All right, 2,100 miles. Right? We're just multiplying 70 times 30 degrees. Okay. All right. Well, where do these numbers come from? Well, 0, it kind of makes sense, and we started at the midpoint between the poles since the poles were natural reference points. But, why is 90 degrees the maximum reading, right? And really what it is just it's simple geometry, right? So those numbers of 10, 20, 30, maximum of 90 is all determined by just simple angular measure. And so, what I'm showing you here is the Earth. And I've drawn in the equator, and then I've drawn in a dot representing the center of the Earth. All right, and now what I need to do is from that dot at the center of the Earth, I'm going to draw an imaginary line outward to the surface of the Earth. And here I've made a dashed line, all right, and I'm just using the northern hemisphere, but it works for the southern hemisphere too. And so here's my imaginary line, all right, and what winds up happening is the angle that is made between that imaginary line and the equator is the latitude at the surface of the Earth. All right, that is it. And so the angle is the latitude, and that actually represents our maximum reading. And so that's why 90 degrees is our maximum reading at the North and the South Pole. All right, let me just give you another example. All right, what I want to do is maybe cut that 90 degrees in half, all right? And let me just make an imaginary line, a dotted dashed line, halfway, all right? And so, again, the angle that is made between my imaginary line and the equator, all right, is going to represent the latitude at the surface, all right? And so right there, all right, we're making a 45-degree angle. So this is half of 90, I'm telling you that. And then what you do is you imagine that the Earth is rotating, all right? And from that point, that 45-degree angle point, you just kind of imagine you got like a giant pen or pencil, and you just, the Earth is rotating, and you draw in the line of latitude all the way around the Earth. All right. Let me just give you another really quick example. All right. Okay. I'm just making a really narrow line with the equator, and here's my imaginary line. And I don't know exactly what it is, but let's just kind of guesstimate that the angle is maybe 10 degrees, or you could say 8 degrees or something like that. And so at that point on Earth, right, is going to be, that's going to be the latitude. And again, you just draw a line all the way around the Earth. And so in this example, I'm saying that is 10 degrees north latitude. And all this works for the southern hemisphere exactly too. Right? I'm just using the northern hemisphere for an example. And so that's where the numbers come from. And that's why 90 degrees is the maximum reading. All right. Okay. And so the geographic grid uses intersecting lines. All right, and so I want to move on to lines of longitude. All right, and these are the lines that run north to south, and just like lines of latitude, they have a second name. All right, they're also called meridians. All right, you can just say meridians of longitude or the 40th meridian. All right, so they just have a second name, and so on Earth, these are the ones that on a map would be drawn north to south, and here we're showing them north to south. But there's one big difference between latitude and longitude, all right? Where latitude lines are perfectly parallel to one another, all right? Perfectly parallel to one another, and you wind up just with a point at the North and the South Pole. Here, these lines are not parallel, all right? They are not parallel. They wind up converging at the poles. Right? And then there's another problem too. Unlike latitude, where we have two natural reference points, the poles, right? Because the Earth spins on its polar axis, if you remember. Here, there's no natural reference point to begin with. Which one would you start with? There's just no rhyme or reason to start anywhere. All right, so there's no natural reference point to begin like we had with starting at the equator. All right, so for a very long period of time, major world powers had their own starting zero line of longitude going through their capital city. all right? And so there are all these different maps where lines of longitude differed. And it was realized that, well, finally, by the 1880s, right, that there had to be a single correspondence, a single world map showing lines of longitude. Right? And so in the 1880s, I believe it was 1886, there was an international conference where all the major world powers got together and decided by international treaty where the zero starting line would begin. And it should kind of make sense that if you think about the colonial era and colonial powers at the time, I mean, England was the major world power. And so it should make sense that the international treaty with the power of England at the time decided that the zero starting line would start at the North Pole and run right through London and cross the equator and then converge on down to the South Pole. But London, even back in the 1880s, was a big city, so you needed to have a specific location in London. And there was a building just outside of London, a suburb called Greenwich. It's just across the Thames River on the you could go across from downtown London, cross on the Millennial Bridge, get into Greenwich, and it's a big tourist location. And now there's the Royal Observatory in Greenwich, London, England, and they've actually got a marker here, all right? And, it's a big tourist location, and there is the zero starting line right there, all right? And like all special lines of latitude and longitude, it's given a name, like the zero starting line for the equator is a special line, it's zero, and the starting line for longitude, that's an important line, so it's given a name. So it's called the prime meridian, all right? And so they've got a marker here, and a lot of people like to go there. You can step right on the zero line. It's kind of a fun thing to do. Or you could put each feet on either side, and you can be in the eastern hemisphere on one foot and the western hemisphere on the other foot. It's kind of a fun thing to do. And so, like I said, Greenwich is, just a suburb of London, just right across the Thames River, all right? And so that's it, all right. Counting lines of longitude, all right? Now here we've got a map, all right, that's just showing the northern hemisphere. It's centered on the North Pole, all right, and it's showing the lines of longitude radiating, away from the North Pole, right? And of course, we're just showing the northern hemisphere, and this would be the equator here, all right? And so what we've got here is, this is not always doing it properly. Okay. Oh, all right. Okay. Let me go back. I'm sorry. Okay. All right. So, the range is zero, all right? So here we've got the North Pole, and there's England, London, England, and that's the zero starting line, and it would continue into the southern hemisphere and converge to the South Pole, all right? Now, since there are 360 degrees in a sphere, it was decided, all right, that the maximum reading of longitude would not be the full circle of 360 degrees. Since latitude divides the Earth into a northern hemisphere, or northern latitudes, and southern hemisphere, southern latitudes, it was decided to take the full circle of 360 degrees and cut it in half. And so we could now create an eastern and a western hemisphere. And so here we go, all right, here's zero, and on the exact opposite side of Earth, all right, the maximum reading going through the Pacific Ocean, all right, is 180 degrees, one half. All right, that's the maximum reading. And so you always count lines of longitude east of London, all right, to a maximum of 180 degrees, or west of London, all right, to a maximum of 180 degrees. That's the maximum reading, okay? And so, like I said, it divides the Earth into eastern longitudes and western longitudes. And one other thing that I do want to point out, again, is our location, all right? In this, map, we can actually see that where, New Orleans is located, right? at 30 degrees north latitude, as we mentioned already. But what about our longitude? All right, you can see that by angular measure, all right, there's London, 0, that we are located, all right, at a 90-degree angle, is that cursor, 90-degree angle, all right, from London, west of London, across the pond, across the Atlantic, and there we are here. And so, the latitude and longitude is really easy to remember, all right? You always start with latitude, so you would say the location of New Orleans is 30 degrees north latitude, comma, 90 degrees west longitude, all right? And so that's the latitude and longitude of New Orleans, all right? And it's just simple geometry, okay? Now, of course, since there's only one 0 line, you don't have to worry about east or west, and there's only one 180 line, you don't have to worry about east or west. But say if you were at 179, right, east longitude, well, then you'd have to say east. If you were at 179 west longitude, then you'd say west, all right? Okay. All right. The thing about lines of longitude, they're not parallel to one another. And so you can't do that simple measuring of latitude as a distance because the lines converge at the poles. And, as it turns out, where you've got the bulge, near the equator, so we can just imagine, let's just pretend that this is, the distance of 1 degree of longitude, even though it's much larger than that, but just pretend it's 1 degree. And so at the equator, the spacing actually works out to be about 70 miles, all right? And by the time you get, all right, to say the Arctic Circle or Antarctic Circle, since the lines are converging, the distance is cut in half, all right, to about 35 miles. And then by the time you get closer and closer to the poles, all right, you're getting down to, the distance of just being 1 foot, 1 inch, and actually, all right, the distance is 0 at the north and the south poles because the lines are touching, they're converging. And so you've got a range of longitude distance measurements between 1 degree of 70 to 0. All right, and so you really can't calculate longitude easily like you can latitude, right? And it is all due to the fact that the lines are not parallel, so we don't have to really worry about calculating longitude. It's a little bit, difficult. There is another thing about longitude, right, that I want to talk about. Longitude lines determine world time zones. All right, and so we're going to talk about longitude and global time. Now, everyone knows that a time zone, time zones in the United States, if you go from one time zone to another time zone, it's a change of 1 hour. All right, you either add an hour or subtract an hour, but everyone knows it's a 1 hour difference. All right, now since there are 24 hours in a day, right, a solar day, there are 24 time zones on Earth. Right. Okay. So how does it work out? All right. Okay. As it turns out, world time zones are centered on lines of longitude, all right, in increments of 15 degrees. And so they're called, these are special lines of longitude. And again, special lines of latitude and longitude are given names. And every increment of a line of longitude of encompassing 15 degrees is a special line, and it's called a standard meridian, all right? And time zones are centered on these standard meridians. So you start at the prime meridian, 0, all right? That's a standard meridian. And then you can go east or west, but let me just go west. Now, there are dashed lines here. This would be the standard meridian, all right? This is our 15 degrees west. And then add another 15 degrees. Another standard meridian would be 30 degrees. Another standard meridian would be 45 degrees. Another standard meridian would be 60 degrees. Now you can see that there's a lot of offset, right, in our lines of longitude. They're not all perfectly, north and south, on this flat map. And the reason why there's a lot of offset is due to, political considerations, countries, all right? I mean, there are countries and counties in the United States that are, states that want to, have this county included, in the single time zone. And so there are huge, variations once you get into politics. And so, but we're still going to use our basic standard meridian increment of 15 degrees. And as it turns out, a 180 on the opposite side of Earth, is, a multiple of 15. So it is also a special line of longitude, and it's a standard meridian. Now, okay. And so the point that I'm making here is that the standard meridians, all right, represent the center of the world time zone, all right? Represent the center. So in reality, right, you would wind up from our standard meridian increment of 15 degrees, and theoretically, we would extend 7.5 degrees to the east of it, and 7.5 degrees to the west of it, and 7.5 plus 7.5 makes 15 degrees, all right? And so that's theoretically. Again, there's big offsets here. But so we still wind up with 15 degrees as a range of time, all right? 7.5 plus 7.5, all right, still winds up being, all right, 1 hour. 15 degrees of longitude represents 1 hour time zone, all right? And so anyways, the thing is, why does a range or a span of 15 degrees, right, represent 1 hour of time, all right? And we have to go back to the fact that one of the first things that I stated in lecture number 1, all right, about a solar day. We know that the Earth rotates 360 degrees in 24 hours, all right? Well, then how much does the Earth rotate every hour? All right, and what you've got to do, right, to find out is you take the 360 degrees and divide by 24 hours to find out how much the Earth rotates, all right, every hour. And the Earth rotates through 15 degrees of longitude every hour, all right? And so that's why, 15 degrees represents a time zone, all right? Okay, and so like I just said, the Earth rotates, 360 degrees in 24 hours, but how much does it rotate every hour, all right? Right now, how far am I into this lecture? 22 minutes. But after 30 minutes, we would have rotated, during this discussion, 7.5 degrees, all right? If I lecture for an hour, we will be rotating, through 15 degrees of longitude. Right? And so that's why time zones are based on 15 degree increments. That's just kind of the magic number. And what I want to do is just to kind of get this straight in your brain, all right? You're all familiar with the time zones of the United States, the lower 48, right? The 4 main time zones of the lower 48. We're not going to include Alaska or Hawaii or anything like that. And so I want to start with the Eastern time zone and move west. All right, and so the time zone is Eastern, and as it turns out, the Eastern time zone is centered on a standard meridian of 75 degrees west of London. All right, and as it turns out, well, New York City is a big city, and that 75-degree line of longitude, runs through New York City. Now, we're just going to pretend that it's noon in New York City. This is just an example. It's noon in New York City based on this example. All right. Now what we're going to do is we're going to move west. Okay. And we know that the next time zone west is our time zone, is the central time zone. All right. And so what you need to know is what the standard meridian is. What is the central time zone centered on? And all you have to do is add 15 degrees. We're moving west from London. All right. We're moving farther away from London, and so what you're going to do is add 15 degrees, and we're moving, further away from London, and so the central time zone is centered right over New Orleans, right? If you remember, the longitude of New Orleans is 90 degrees west. All right. Now, since we're moving west, all right, it's getting earlier. All right. It's going to be 11 a.m. That's something we're going to talk about in just a few seconds. All right. And then, as you probably know, the next time zone is the mountain time zone, still moving further west from London. All right. And so it's going to be centered on a standard meridian. And we're going to add 15 degrees, all right, to 90, moving farther away. And our standard meridian, the center line of the mountain time zone, is 105 west longitude. It runs through Denver, and it's getting earlier, all right, so it's 10 a.m. And then, the final time zone of the lower 48 is the Pacific time zone. And again, it's going to be centered on the standard meridian of 120 degrees further west, and it runs through the big city of Los Angeles, all right? And it's going to be much earlier, all right, in LA. It's going to be 9 a.m. And you might be familiar with this just watching TV and the news and things like that. I mean, it's always much earlier, in Los Angeles if they have the news in New York City, all right? It's always much earlier, all right? And so let's take a look at the time zone map. Okay, the time zone map from our textbook, and it's showing our standard meridians. All right, here's 75 is kind of the center line theoretically for the Eastern time zone. Again, there's political considerations here, so there's deviation. And there's the 90 degrees, all right, for our central time zone. And again, it's not perfect because of political considerations. And let's see, I don't know if we can see Denver. Yeah, right there. There's Denver, all right. It's 105, and there's the 120 center line for the Pacific, okay. And so, anyways, what I want to do now is talk about, adding and subtracting. Which way do you go? All right. And so I want to ask you the question, just based on the table, and we're just pretending it's noon in New York City, all right? Can we figure out what time it is in London? We can, all right? And what you need to do is you need to know the amount of longitude between these two locations. All right. Now, London is way across the, Atlantic, about way over here, and we know the longitude of London, don't we? All right. It's 0. It's where the prime meridian is. All right. And so the range of longitude between London and New York City is 0 and 75. Okay. And so we now know that the range of longitude between these two locations is 75 degrees of longitude, all right? We want to know now how many hours, all right, separate New York City and London, all right? So you take that 75-degree range that we know, and what do you divide it by? 15, all right? And so we know that London is 0 degrees longitude. We know that New York City is 75 degrees west, all right? So the range between the two cities is 75. You divide it by 15 because 15 degrees is the magic number. I mean, that's 1 hour to find the hours. So you do the division. 75 divided by 15 is 5 hours, okay? Now, the important thing to know, we've got to go back to one of the first things we learned, is the direction of the Earth's rotation. The Earth is rotating west to east, all right? And right now in this diagram, New York City is directly facing the sun, all right? So it's noon, directly facing the sun. And so, we still have, time, hours for these other locations west of New York City to rotate to directly face the sun, all right? And so we still have an hour for the central time zone to rotate directly to the sun, all right? And so we're at 11 a.m. And, all right, still further away, Denver, all right? We're still further west, and we still have to rotate now through 30 degrees of longitude to directly face the noon sun. All right, and it all has to do with the west-east rotation. Again, the Pacific is still much farther away west, and we've got to rotate, right, and rotate and rotate to get to directly facing the sun to make it noon. All right, so if you travel west, it's always going to be earlier because you still got to have the Earth rotating directly to face the sun. Okay, now what about east of New York City? Well, it's past noon. All right, it's already rotated past directly facing the sun, and so in every 15-degree increment, all right, it's going to be later and later. It's already rotated, and so our conclusion is, right, since we're traveling across the Atlantic, all right, eastward, if you travel from New York City to London, all right, it is going to be 5 hours later, all right, and it's going to be 5 p.m. in London. And that concludes lecture number 2.